Hello friends, welcome to engineering tutorial. We have already finished some of the basic concepts related to PN junction diodes. We discussed the various concepts such as forward biasing, reverse biasing, voltage current characteristics, these equivalent circuit models of a PN junction diode in my previous videos. So in the next few videos, we will try to understand some more concepts related to diodes with the help of some numerical problems. Okay, some numerical problems we will try to understand the various concepts associated with them, the application of the concepts by solving these numericals. So here this is a question related to PN junction diode where it has been asked to determine the state of this diode, okay, whether it is on or off, or whether it is forward biased or reverse biased. Now whenever you come across a PN junction diode connected in a circuit and you have to determine its state, I have already told you that rarely you will find a straightforward circuit, whether you can just say by looking at the circuit whether it is forward biased or reverse biased. So in those type of questions you have to take the help of assumptions. Okay, so there are two approaches to this. We will discuss both of them separately. So in the first approach, the first method, you can assume that this diode is either forward biased or on, or reverse biased or off. Now let us first assume in method 1 that this diode is off, means it is open circuited. So let us redraw the circuit. Okay, this is the plus minus the 2 volt voltage source, this is the 4 kilo ohm resistance, this is the 1 kilo ohm resistance. Now we have assumed that this diode is off. Okay, this is 4 kilo ohm, this is 1 kilo ohm, 2 volt. So we have assumed that this diode is off. We have replaced it with a open circuit. Now let us calculate the voltage across these two terminals. Let us name it A and B. Now the voltage across the terminals A and B is the same as the voltage across the resistor 1 kilo ohm, isn't it? The voltage across the two terminals A and B is the same as the voltage across the resistor 1 kilo ohm. Now this voltage we can calculate by applying voltage division rule. You can see as this is open circuited, 4 kilo ohm and 1 kilo ohm are now in series with the 2 volt voltage source. So let us calculate the voltage across 1 kilo ohm. So the voltage across the 1 kilo ohm resistor is equal to 2 into 1 by 1 plus 4, which is equal to 2 by 5, which is equal to 0.4 volt. So the voltage across the two terminals A and B is 0.4 volt. Now here it has not been mentioned whether the diode is silicon or germanium. Now remember one important thing, whenever nothing is mentioned in the question about the cut-in voltage of the diode, whether it is a what type of diode it is, whether it is a silicon diode or a germanium diode, you have to consider that it is silicon by default. Okay, you have to consider that it is silicon diode by default. Okay, so here we will consider that it is a silicon diode, and the cut-in voltage of a silicon diode is 0.7 volt. Okay, 0.7 volt. So whenever nothing is mentioned about the type of diode in the question, okay, here nothing has been mentioned whether it is a silicon diode or germanium diode or any other semiconductor diode, and there has been no mention about the cut-in voltage of the diode. So you have to go by the assumption that it is a silicon diode and it has a cut-in voltage 0.7 volt. Now the voltage across the two terminals A and B is 0.4 volt. Okay, we calculated it by voltage division rule. Okay, voltage division rule. Now this 0.4 volt is obviously lesser than 0.7 volt. Okay, so this is not sufficient to turn this diode on. So it is not sufficient. 0.4 volt is lesser than 0.7 volt, it is lesser than the cut-in voltage. So the state of the diode in this circuit is off. It will be off. This diode is off. Diode D is off, as VAB, or the voltage across the P and the N terminals, okay, this is the P, this is the N, is equal to 0.4 volt, which is lesser than 0.7 volt, which is the cut-in voltage of the silicon diode. Okay. Now we will also discuss the second method of approaching this numerical problem, where we will assume that the diode will be on. Okay. So we will discuss that method too. So this is the second method of solving the same circuit to determine the state of the diode D. Okay, so here we will assume that the diode is on, and by assuming that the diode is on, it means that it will replace it with its equivalent circuit model, which is the simplified model. So we will just replace it with its cut-in voltage, which is 0.7 volt. So let us redraw the circuit. Okay, so again the 2 volt voltage source, the 4 kilo ohm resistance, followed by the 1 kilo ohm resistance, and here we will replace the diode with its cut-in voltage, okay, in this form, this 0.7 volt. This is 4 kilo ohm, this is 1 kilo ohm, this is 2 volt. Now please pay attention here. Whenever you replace the diode with its cut-in voltage, make sure that the p-type end is given with the positive terminal of the voltage source. It is replaced with the positive terminal of the voltage source, and the n-type end is replaced with the negative terminal. Okay, the p-type end should be replaced with the positive end, and the n-type end should be replaced with the negative end. The voltage source should be in this direction when the diode is in this way. Okay, so we have replaced it with its cut-in voltage, which is 0.7 volt. I have already told you that whenever nothing is mentioned about the type of diode or about the cut-in voltage, you have to go in with the assumption that by default it is a silicon diode, and silicon diode has a cut-in voltage 0.7 volt. Now let us assign some current directions. Let this current be ID, okay, the current flowing through the diode. This current be I1 and this current be I2. Okay. Now the voltage across this 1 kilo ohm resistance is 0.7 volt. You can see the 1 kilo ohm resistance is connected across the 0.7 volt cut-in voltage, which we have replaced the equivalent circuit of the diode. So the voltage across this 1 kilo ohm will be 0.7 volt. Okay. So if we apply KVL in this loop, we will get the KVL equation as 2 minus 4I1 minus 0.7 is equal to 0. That implies 4I1 equals to 2 minus 0.7, which is equal to 1.3. That implies I1 is equal to 1.3 by 4 milliampere. So let us calculate how much this value is by, let me just calculate it. 1.3 divided by 4 is equal to 0.0 1.3 divided by 4, 0.325. Okay, it's 0.325 milliampere. This is 0.325 milliampere. Okay, so we have calculated it. We have put KVL in this loop, which is this equation, 2 minus 4I1 minus 0.7 is equal to 0. This 0.7 is the voltage across this 1 kilo ohm resistance. So we got the value of I1 as 0.325 milliampere. Now, the current I2 can be determined by this equation. I2 is equal to 0.7 by 1 kilo ohm, which is equal to 0.7 volt by 1 kilo ohm, which is equal to 0.7 milliampere. Okay, you see the voltage across the 1 kilo ohm resistance is 0.7. Okay, the voltage across the 1 kilo ohm resistance is 0.7. So the current flowing through that resistance I2 will be 0.7 by 1 kilo ohm. Simple Ohm's law. Okay, we applied simple basic Ohm's law. Now we have to apply KCL here. What the KCL says, that the total summation of the currents across any node is 0, or the current entering the node and the current exiting from the node will be the same. So let us write the KCL equation. Here the current entering the node is I1 and the two currents exiting from the node are I2 plus IT. So I1 is 0.325 milliampere, ID is 0.7 milliampere, sorry, I2 is 0.7 milliampere plus ID. ID is the unknown value. Now we can calculate ID is equal to 0.325 minus 0.7. Now let us just calculate it with the help of the calculator. 0.325 minus 0.7 is equal to minus 0.375. Negative current. Now here is the main concept applies, or we will study the main concept. Whenever you assume that a diode is on, okay, whenever you assume that a diode is on and you replace it with its equivalent cut-in voltage, if, okay, 0.7 volt, this is the equivalent circuit model of this diode, okay, in this direction. Here we found out the current flowing into the diode is negative current. Whenever the current flowing through the diode comes negative, okay, whenever the current flowing through the diode is negative, which is in this case in this direction, I'll make note of this direction. Whenever the current flowing through the diode in this way, from the positive to the negative internally, or from P to N direction, whenever current flows in this direction and the value comes negative, you can say that the diode is off. Okay, whenever the current flowing through the diode comes negative, you can say that the diode is off. if this value would have been plus 0.375 milliampere, okay, if this diode current would have been plus 0.375 milliampere, then we could have said that this diode is forward biased, it is on. So here our assumption that this diode is on is wrong, because the current flowing through the diode from P to N, the current flowing through the diode from P to N in this direction is negative, it is coming negative. So the actual direction is in this direction, the actual current direction is in this, because it is negative. So this diode is off, our assumption was wrong. So whenever you come across a circuit where you assume that a diode is on and you calculated the current flowing through the diode and the value came negative, whatever may be the magnitude, if the sign is negative, then you can say that the diode is off. Okay. So this is the second method of approaching circuits associated with PN junction diode, where you have to determine the state